Hello, space enthusiasts and curious minds. Welcome back to our channel, where we dive deep into the cosmos and bring the universe closer to you. Today, we're embarking on an extraordinary journey through time and space as we discuss a groundbreaking discovery by the James Webb Telescope, one of the oldest galaxies ever observed. Stick around as we explore the significance of this find and what it means for our understanding of the universe. Michio Kaku once said, "We may need to rewrite all the textbooks on the beginning of the universe. Imagine it takes billions of years to form a galaxy like the Milky Way, which is home to over 100 billion stars. Yet, the James Webb Space Telescope has unveiled a startling discovery: 6 galaxies that emerged a mere 500 million years after the Big Bang, each up to 10 times larger than the Milky Way. This revelation challenges everything we thought we knew. There's no going back now. The James Webb Telescope has not only spotted one of the oldest galaxies known to us, but also found it to be incredibly vast and bright, far beyond what we'd expect from the early cosmos. This giant leaps beyond traditional cosmic timelines, pushing Michio Kaku to suggest that we're on the brink of a revolutionary era in physics. This could pave the way for groundbreaking theories like string theory and the multiverse to solve the Hubble tension, an ongoing discrepancy in measurements of the universe's expansion rate. Kaku humorously remarks on these groundbreaking observations by the JWST, highlighting that these massive advanced galaxies shouldn't exist so soon in the universe's timeline. Yet here they are, defying expectations. Ever since the Big Bang was first theorized, there have been discrepancies between what we expect and what we observe. You might be familiar with the Hubble tension, a persistent challenge in accurately measuring how fast the universe is expanding. This puzzle has baffled scientists since the 1990s and remains unsolved. Now, the James Webb Space Telescope is unveiling even more complexities that challenge our grasp of cosmology and astrophysics. Michio Kaku has raised an intriguing point. The Big Bang, said to have occurred 13.8 billion years ago, might need rethinking. Astonishingly, just 250 million years later, galaxies were already bustling through the cosmos, galaxies that were larger than our Milky Way, contradicting our current models of how galaxies evolve. According to those models, it takes billions of years to form galaxies like ours. But Webb didn't stop there. It has revealed dozens of these ancient, large, and intricately structured galaxies, each one presenting a new riddle for astronomers. Moreover, Webb has captured images of colossal black holes, each with over 1 billion solar masses, existing merely 500 million years after the Big Bang. These revelations challenge the very fabric of our scientific understanding, suggesting that our theories might be profoundly flawed. The launch of the James Webb Space Telescope has precipitated a major crisis in modern cosmology, potentially 10 times more significant than any previous challenge in the field. Michio Kaku can't help but chuckle when he talks about some of the galaxies recently discovered by the James Webb Space Telescope, which appear up to 10 times larger than the Milky Way. The esteemed American astrophysicist, long vocal about the significant gaps in our scientific theories, has championed the idea of merging quantum field theories with the astrophysics of grand phenomena like stars and galaxies, a notion that wasn't always well received in more traditional scientific circles. Now, those very traditionalists face a daunting challenge as their rigid views on the cosmos and the theories surrounding the evolution of matter and the Big Bang are being shaken to their core. With Webb's latest discoveries, we stand on the brink of a new era in physics, poised to uncover entirely new facets of our universe. The skeptics can hardly claim surprise, even before Webb, the Hubble Space Telescope, and other observations had already cast doubt on the conventional narrative of the Big Bang and cosmic expansion. Among these pivotal findings was the discovery of a galaxy known as GZ9P3 by the Hubble. Hubble only managed to detect this galaxy as a faint point of light, hinting at the vast mysteries lying beyond our current understanding, waiting in the depths of the supposedly early universe. The faint spot of light, once an enigmatic blur, has finally been unraveled by the James Webb Space Telescope. A deeper investigation into GZ9P3 revealed that this was not just any celestial object but a very old galaxy, emitting light from an era merely 5–10 million years post-Big Bang. Under Webb's discerning gaze, this galaxy exhibited a redshift of Z9.3, a staggering implication that we are peering back into the infancy of the universe. Yet GZ9P3 is no ordinary primordial galaxy. It's far more massive and developed than anything we'd expect from such an early era. Its structure alone has left scientists pondering, showcasing a peculiar formation with two luminous spots, indicating two dense cores. This unique configuration suggests that we might actually be observing not one, but two merging galaxies, a rare cosmic event in what was thought to be the early universe. The notion of primordial galaxy mergers challenges our foundational understanding of cosmic timelines. Traditionally, it's believed that it takes billions of years for galaxies to evolve to such advanced stages. Yet here we are, witnessing this galactic spectacle as it appeared just 510 million years after the Big Bang. These findings compel us to reconsider our theories about the universe's youth and the speed at which its celestial bodies can mature. This galaxy, dominated by young bright stars, also harbors elements like silicon, carbon, and iron, traces typically linked to older stars. These elements are signatures of advanced stellar evolution, not something you'd expect to find in a galaxy that's supposed to be in its infancy. Clearly, there's a mismatch here, and it raises a big question. Are we truly looking at a young galaxy? The presence of these older elements implies that stars began forming and enriching the universe with metals much earlier than previously thought, suggesting that GZ9P3 may have chemically matured at an unprecedented rate. Alternatively, we might be misunderstanding the age of the universe altogether. This brings us back to the Hubble tension, a thorny issue questioning the very fabric of cosmic expansion. Did you know the expanding universe theory has never been definitively proven? While significant evidence supports this cornerstone of modern cosmology, which burst onto the scene in the 1920s much like a revolution, discrepancies soon emerged. Just as the James Webb Space Telescope is reshaping our current worldview, it's crucial to reassess what we think we know about the universe. Let's delve deeper into the evidence that underpins this theory, its challenges, and what recent observations might mean for our understanding of cosmic history. The first hint that the universe might be expanding came from the pioneering observations of Vesto Melvin Slipher, an American astronomer working in the early 1910s. While studying the spectral lines of galaxies, Slipher noticed many exhibited a redshift, suggesting they were moving away from us. This was a curious find, but the true breakthrough didn't arrive until 1929, when Edwin Hubble, another luminary in American astronomy, took these observations further. Utilizing the Doppler effect, which explains how the frequency of light or sound waves changes for an observer moving relative to the source of the waves, Hubble made a groundbreaking discovery. He found that the farther a galaxy was from us, the faster it appeared to be moving away. This relationship, now known as Hubble's law, became the cornerstone of the theory that the universe is expanding, a concept that fundamentally changed our understanding of the cosmos. Yet, the expansion of the universe isn't just supported by redshifts. Another compelling piece of evidence is the cosmic microwave background, CMB, the remnant radiation from the universe's early moments, about 380,000 years after the Big Bang. Discovered in 1965 by Arno Penzias and Robert Wilson, the CMB's remarkably uniform temperature distribution across the vastness of space further bolsters the case for an expanding universe. This radiation, dispersed uniformly across the universe, serves as a powerful testament to a time when the cosmos was significantly denser and hotter, indicating that it has been expanding from that state ever since. Another compelling piece of evidence supporting the expansion theory is Big Bang nucleosynthesis. This theory explains the formation of light elements such as hydrogen and helium in the early universe, and remarkably, their present abundances align closely with what we would expect from an expanding universe. Despite these strong indicators, the theory of cosmic expansion isn't without its contradictions and unresolved issues. One of the most notable is the Hubble tension. This term refers to the inconsistencies that arise when different methods are used to measure the rate at which the universe is expanding. For example, satellite observations of the cosmic microwave background, CMB, such as those conducted by the Wilkinson Microwave Anisotropy Probe and the Planck Space Telescope, consistently yield a Hubble constant in the range of about 67 to 68 km/s per megaparsec. Contrastingly, another method involves using standard candles, like Cepheid variables and Type Ia supernovae. Cepheids are pulsating stars, the brightness of which allows astronomers to establish fixed points for measuring cosmic distances and velocities. This method tends to produce higher estimates of the Hubble constant, further fueling the debate and adding layers of complexity to our understanding of how the universe truly behaves. The luminosity of Cepheid variables is directly linked to their pulsation periods, while Type Ia supernovae have a standardized brightness. By gauging their apparent brightness, astronomers can determine distances. These measurements, when combined with redshift data, allow for the calculation of the universe's expansion rate. Intriguingly, this method typically results in a higher Hubble constant, around 73 to 74 km/s per megaparsec, adding another layer to the cosmic puzzle. Several theories have been floated to explain this discrepancy. It could be a result of systematic errors in measurement techniques or foundational assumptions, leading to skewed results. Many scientists also wonder if there might be gaps in our understanding of dark matter and dark energy, which are believed to constitute the vast majority of the universe. Yet, despite their significance, these mysterious components remain largely unmeasured and elusive, clouding our understanding of their true nature. Recent observations by the James Webb Space Telescope have even led some researchers to propose that dark matter and energy might alter their properties over time, making them fundamentally unmeasurable or indeterminable. If this is the case, achieving a complete scientific description of the universe may be an elusive goal. However, there are other theories regarding the Hubble tension. The variability of standard candles could be influenced by their environments, making them unreliable markers for measuring cosmic distances. As we delve deeper into these mysteries, it seems we may be on the brink of a new era in physics, one that will reshape our understanding of the cosmos. Here's a more engaging rewrite of that script section. The observed drifting apart of certain regions within the cosmos is undeniable, yet the question remains, is the entire universe uniformly expanding? Current observations of areas experiencing slower expansion rates or phases where the expansion accelerates suggest that the universe is a dynamic entity with varying behaviors across its vast expanse. This complexity indicates that our cosmos might not conform to a singular origin story. Enter Michio Kaku, a visionary physicist who thrives at the intersection of crisis and opportunity. Known for his eloquent ability to demystify complex scientific ideas, Kaku has long challenged conventional cosmological theories. In his view, the multiverse isn't just a possibility, it's the most probable reality. A cosmos where multiple universes exist, each governed by potentially unique physical laws. The James Webb Telescope has done it again. This marvel of modern astronomy has peered back over 13 billion years to bring us images of an ancient galaxy. This find is not just old, it's one of the earliest galaxies formed after the Big Bang, making it a crucial piece in the cosmic puzzle. How does discovering such an ancient galaxy help astronomers? It provides a unique look at the building blocks of the universe, offering clues about how galaxies form and evolve. Discovering one of the oldest galaxies illuminates the path of cosmic evolution from the Big Bang to the present. Such galaxies are rare windows into the early universe, showing us the conditions and processes that prevailed at that time. By studying this galaxy, scientists can better understand the rate at which the universe expanded and how the first stars and galaxies came into existence. Each observation adds a piece to the story of our cosmic origins. The James Webb Telescope, with its advanced technology, is designed specifically to look further into space and further back in time than any telescope before it. Its powerful instruments can capture light that has traveled for billions of years before reaching us, light from the time when the universe was just a few 100 million years old. This capability is what allows us to see such ancient cosmic entities today. Observing these ancient galaxies is no easy feat. It involves a complex interplay of pointing the telescope in the right direction, long exposure times to collect enough faint light, and then using sophisticated algorithms to interpret the signals collected. Scientists spend months, if not years, planning, executing, and analyzing these deep space observations to ensure they are capturing and interpreting the data correctly. This discovery by the James Webb Telescope opens up new avenues for research and raises as many questions as it answers. What were these ancient galaxies like? How did they influence their environment? And what can they tell us about the future trajectory of our own galaxy? These are just some of the questions that astronomers will be eager to explore in the coming years. The James Webb Telescope is just beginning its mission to uncover the secrets of the early universe. Future observations are planned to target other similarly ancient galaxies, helping to build a more comprehensive picture of the universe's infancy. This will not only enrich our understanding of galaxy formation, but will also refine our models of cosmic evolution and the overall timeline of the universe. What makes the James Webb Telescope uniquely capable of these observations? Its suite of scientific instruments, including near-infrared cameras and mid-infrared sensors, allow it to detect the faint light from distant galaxies. These technologies are the culmination of decades of astronomical research and engineering, designed to operate in the extreme conditions of space. Infrared astronomy is crucial for observing the distant universe. Many of the signals from the earliest periods of the universe are stretched into the infrared range of the electromagnetic spectrum by the time they reach us, due to the expansion of the universe. This makes infrared telescopes like James Webb invaluable tools for peering into our cosmic past. The discovery of one of the oldest galaxies is not just a triumph for the James Webb team, but also a shining example of international collaboration in space exploration. Teams from around the world contribute to the operations of the telescope, analysis of data, and the dissemination of findings, demonstrating the global nature of astronomical research. Such groundbreaking discoveries have significant educational implications. They provide an excellent opportunity for educators to introduce students to advanced concepts in physics and cosmology, inspiring the next generation of scientists. Schools and universities can use these findings to update curricula and provide more current and exciting content for students. Each discovery like this fuels public interest and excitement in space exploration. Public engagement is crucial for the continued support of space missions, as it drives funding and interest in STEM fields. This interest also leads to a more informed citizenry, capable of making educated decisions about science policy. Observing distant galaxies is fraught with challenges. The faintness of the signals, the need for precise instrument calibration, and the interpretation of vast amounts of data all pose significant hurdles. Each successful observation is a testament to the advancements in technology and our growing expertise in handling complex space missions. This ancient galaxy from the universe's dark ages, a period shortly after the Big Bang when the universe was mostly dark, helps fill in gaps about this mysterious era. Understanding the dark ages is key to comprehending the evolution of the universe from a smooth, dark state to the complex, star-filled cosmos we see today. Discoveries like this also have implications for theoretical physics. They provide real-world data that can either support or challenge existing theories about the nature of dark matter, dark energy, and the overall dynamics of the universe. Each observation can lead to refinements in our theoretical frameworks. Studying one of the oldest galaxies also gives insights into galactic interactions and their roles in galactic evolution. How did early galaxies influence one another? How did collisions and mergers shape the universe? Observations like these provide crucial data for understanding these processes. The spectral analysis of light from this galaxy helps astronomers determine its composition, temperature, density, and motion. This data is crucial for building accurate models of early galaxies and understanding the physical processes that govern the early universe. The James Webb Telescope's observations contribute to mapping the cosmic web, the large-scale structure of the universe made up of galaxies and gas. This structure forms the backbone of all cosmic formations, and understanding its early stages is key to comprehending the layout of the universe. Gravitational lensing is another area where observations of ancient galaxies play a crucial role. This phenomenon, where the gravity of a foreground object warps the light of a background object, can magnify distant galaxies, making them easier to study. It's a natural cosmic telescope that James Webb can exploit. The data from James Webb is shared with the global scientific community, fostering an environment of open science. This accessibility accelerates the pace of discovery and innovation, as researchers around the world can work with the data to make new discoveries and verify findings. Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos, and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together, we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.